Hi everyone. Welcome to the ILTA Physics problem solving session. The problems we're going to tackle today are all about the law of conservation of momentum. As you can see in the diagram, even when two cars collide and their individual velocities change, the total momentum of the entire system remains constant before and after the collision. That is the core of the law of conservation of momentum. What's really interesting is that no matter what happens inside the system containing those two cars, the total momentum is conserved. In other words, whether it's a collision, an explosion, or an ejection event, the momentum before and after the event stays the same. The types of collisions we'll be looking at today can mostly be categorized into elastic and inelastic collisions. And we will also solve some problems by thinking of explosions and ejections as the reverse process of collisions. Now, let's briefly summarize the theoretical concepts behind the law of conservation of momentum. Some of you might recognize the diagram on the right from your theory lessons. Two balls are moving toward each other, and at the brief moment of impact, they exert forces of equal magnitude but in opposite directions on one another. This is Newton's third law, action and reaction. After the collision, the diagram shows the two balls then moving in directions opposite to their initial motion due to those forces. I want to explain the law of conservation of momentum using this specific collision scenario. First, let's think about ball number 2 on the right at the moment of collision. Based on the formula we learned earlier, impulse is calculated as the product of the force and the time interval of the collision. According to the impulse-momentum theorem, this impulse results in a change in momentum for ball number 2. Now, let's apply the same physical logic to ball number 1 on the left. The impulse acting on ball number 1 is the product of the force acting to the left and the time interval. This shows up as a change in momentum for ball number 1 according to the impulse-momentum theorem. Since ball number 1 is moving to the left, we use a minus sign to represent its physical quantities as negative values. Now let's connect the physical events happening to both balls. In this collision, the impulses received by the two balls are equal in magnitude and opposite in direction due to Newton's third law, so-called the action-reaction pair. By connecting these equations, we can see that the change in momentum of ball number 1 is equal in magnitude and opposite in direction to the change in momentum of ball number 2. Put simply, a decrease in momentum on one side appears as an increase in momentum on the other side. Therefore, the momentum before the collision and the momentum after the collision for the entire system are always the same. This is what we call the law of conservation of momentum. Mathematically, we can say the total initial momentum before the collision is equal to the total final momentum after the collision. In actual problems, since momentum is the product of mass and velocity, the expanded equation looks like this. The sum of mass times velocity for all objects before the collision equals the sum of mass times velocity after the collision. Please note that we usually use the prime symbol to denote velocities after the collision. This formula will be applied to every single problem we solve today regarding the conservation of momentum. When objects collide, there are a few things to consider to apply the conservation of momentum correctly. Generally, after two objects collide, they either stick together and move as one mass, or they move separately as two individual objects, like in the diagram on the right. Depending on these two cases, the way we calculate the mass after the collision changes. First, the case where two objects stick together and move as one unit is called an inelastic collision. In this case, the final mass is simply the sum of the two individual masses. On the other hand, if the two objects move in different directions after the impact, it's an elastic collision. When calculating momentum here, you just plug the individual mass values into the equation separately. Finally, physical phenomena like explosions or ejections can be interpreted as the reverse process of a collision. From the perspective of conservation of momentum, an explosion or ejection event starts with two objects joined together, usually at rest. Let's call these two objects A and B for convenience. Since they are at rest before the explosion, their velocity is zero, which means the initial momentum is also zero. If object A is exploded or ejected, object B will move in the opposite direction. Remember that in explosions or ejections, the two objects generally move in opposite directions. Please keep in mind that the two objects moving in opposite directions means that the calculated velocity values for each object will have different mathematical signs. If any of these brief theoretical points are confusing, I recommend going back to my theory lecture first before moving on to the problem solving. Alright, let's start solving some problems related to the law of conservation of momentum. Problem number 21 is about an elastic collision. A 3-gram bullet is flying at 500 meters per second and passes through a 2.7 kilogram wooden block sitting on a frictionless table. If the velocity of the bullet after passing through is 220 meters per second, what is the velocity of the wooden block? This is a classic two-body collision problem. First, the problem mentions the wooden block is on a frictionless table, which means we don't need to worry about friction affecting the motion. We can solve this easily by using the law of conservation of momentum, which states that total momentum before and after the collision is equal. One more thing to recognize is that this is an elastic collision because the bullet and the block do not stick together. They move in different directions after the impact separately. When I say different directions here, it doesn't just mean their actual paths are different, but rather it covers any case where they move as separate entities after the collision. Now, let's find the total momentum before the collision. Using the momentum formula, we can calculate the total initial momentum of the bullet and the block. In physics problems, the common phrase, at rest, is a condition that means the velocity is zero. In this problem, since it says the block is on the table, it is at rest. Therefore, the initial velocity of the block is zero. We can calculate the momentum after the collision the same way. To emphasize once again, in this problem, the bullet passes through the wooden block, so it is an elastic collision. Therefore, the total momentum after the collision is calculated as the sum of the products of each mass and its respective velocity for both the bullet and the block. Again, we use the prime symbol for the final velocities. Because the momentum before and after must be equal, the velocity of the wooden block after the collision comes out to 0.31 meters per second. This is a very fundamental and typical elastic collision problem. If the bullet had become embedded in the wooden block and they moved together as one, you would solve this as an inelastic collision problem. Problem number 23 is a typical inelastic collision type. A 10,000 kilogram train is moving at 2 meters per second when 400 kilograms of gravel are dropped into it. We need to find the velocity of the train with the gravel after this happens. In this problem, gravel is being added to the train, so the two move together as one mass after the collision. This is an inelastic collision. Therefore, we apply the conservation of momentum and account for the fact that the two objects become a single unit. The total momentum before the collision is the product of mass and velocity, and the initial velocity of the gravel is zero. The total momentum after the collision is the combined mass of the two objects multiplied by their shared velocity. According to the law of conservation of momentum, the velocity of the train carrying the gravel is 1.43 meters per second. It's just like the previous problem, but since it's inelastic, you just have to be careful that the two objects move together at the same velocity after the collision. Problem number 24 is about an ejection. A jellyfish takes in water and then squirts it out to move forward. The mass and velocity for both are given in the problem. Ejection can be viewed as the reverse of a collision, so the law of conservation of momentum still applies. One thing to watch out for is that in most explosion or ejection problems, the system starts at rest, so the initial velocity and momentum are both zero. After the ejection, the two objects move in opposite directions. Let's calculate the initial momentum first. Since the jellyfish is initially at rest, its velocity is zero, making the initial momentum zero. The total momentum after squirting the water can be expressed as the mass of the jellyfish times its velocity, plus the mass of the ejected water times its velocity. Using the law of conservation of momentum, the velocity of the water after ejection is minus 0.102 meters per second. Notice that the velocity is negative. This physically means the water is moving in the opposite direction of the jellyfish. The physical phenomenon is different, but the conservation of momentum we studied applies exactly the same way. Problem number 25 is a classic explosion problem. When a hunter fires a gun while standing on frictionless ice, the bullet moves forward and the recoil pushes the hunter backward. Again, think of an explosion as a reverse collision. We apply the conservation of momentum where the initial total momentum equals the sum of the individual momenta after the explosion. Usually, everything is at rest before the explosion, so the initial momentum is zero. Remember, the bullet and the recoiling hunter move in opposite directions. Since they start at rest, the initial velocity is zero, and the total initial momentum is also zero. The total momentum after the explosion is the sum of the mass-velocity products for both the hunter and the bullet. By the law of conservation of momentum, the hunter's velocity is minus 0.47 meters per second. Take note that the hunter's velocity is negative. This represents the physical reality that the hunter is moving in the opposite direction of the bullet. That's it for today's lecture. Great job, everyone. I'll see you next time.